Alright, so this is part 2 of our interference videos. In the last video, we left off looking at the idea of diffraction and how light, or any other way for that matter, bends and spreads out when it is met with an obstacle or a gap, right? And that allowed us to see how a singular source of light can be put through double slits and therefore produce an interference pattern on a screen, and we can get regions of light spots and dark spots. So for this video, we're going to be continuing on with the double slit experiment, and we want to look at some of the angles and geometry that are involved in this double slit experiment. Okay, so first off, I want to draw a double slit diagram, right? And in this, I'm going to draw two light waves, okay, that are coming off like this, and these two light waves are parallel, okay, coming from each slit. And I want to draw your attention to this perpendicular line right here, okay? So that obviously makes a right angle right here, and this distance right here is very important. This is our path difference, right? We can see how this is our path difference because over here in our top slit, that is where the light rate sort of starts. However, if we draw a perpendicular line straight down, we can see that in the bottom slit, the same location is sometime after the ray has started for the bottom slit, right? So we can see that there is a path difference there. So that's why we have labeled that the path difference. And we can also call the slit separation, so the distance between the two slits, D, all right? So D is our slit separation, okay? And so from this, we can make a relationship between the path difference and our D value, our slit separation. So like I said, this is a right angle, so we can sort of make a right angle triangle here and call this angle theta, okay? And so from here, using our trig, we can get that the path difference is equal to d sine theta, okay? Right, if you remember back to our previous video, we said that the path difference is equal to n lambda. So therefore, n lambda is equal to d sine theta. And that is the equation that you have probably seen in your formula sheet. Okay, so now that we got that out of the way, let's go over here and draw an even larger double slit, okay? And let's pick an arbitrary point of a bright spot right here, okay? So imagine we have our wall there and we have a bright spot over here, okay? Like we stated over here, because of how small the distance is between them, mathematically, these two light rays can be thought of as parallel, okay? And again, we have our same geometry where we have a right angle here, and we have an angle here, and our path difference is equal to d sine theta, okay? However, we know from our previous video that eventually these light rays converge to a single point, right? A bright spot, okay? Eventually these light rays come in, okay? This is just like a slice, okay? I'm just making a shortcut. These light rays come in and converge. Now, how is this possible? On the one hand, we're saying that light rays are parallel, and on the other hand, we're saying that they converge. Now, we know that two parallel lines can never converge because they're parallel with each other, right? So, how can we say that on one hand they're parallel, but on the other hand they converge? All right, let me explain that. Now, this is largely due to the scale that we're working at here, right? You can imagine the scale that we're working at here is very, very small. Now, like I said previously, we have constructive interference at this point, okay? And so you can imagine that this path difference, we can imagine, let's say for arbitrary purposes, that this is one wavelength, okay? So we have drawn in a wavelength, and so this path difference is equal to one wavelength, okay? So therefore, as our n value is 1, we are in phase, and therefore resulting in constructive interference, okay? Okay, so now why can we assume parallel lines, but then the parallel lines converge, okay? Let's get into that. Let's draw our double slit once more, and we have our wall on this side, okay? So we can draw a dotted line through here. Now let's label this distance right here, L, so our distance L, and obviously, again, like I said, this is our wall, and this is our slits, okay? And we have our laser light coming through here, okay? So this is our light waves here, okay? There we go. Now, L is obviously, again, in meters, right? Now, again, we know from our previous video that we are going to have a bright spot right here. This is our n is equal to 0, and that's our central maximum, okay? And this is obviously a bright spot, okay? Or we can put fringe, bright fringe, it's the same thing. And again, the reason behind this is because we will have two light rays converging onto here, and the distance that these two light rays have to travel are equal, and therefore that results in the path difference being 0, and therefore that's a whole number, and so we get constructive interference and therefore a bright spot. And so obviously, again, we have a bright spot up here, we know that, and a bright spot down there matching on the other side. And so this is obviously our n is equal to 1. Again, another bright spot. Therefore, there is constructive interference here. Okay, and obviously we have the same thing on this side, n is equal to 1. So this is the case that we're going to look at. We have our light rays coming through, okay, like this, and converging to this point. And we obviously have the same geometry that we had before, where this is the right angle, and we have a path difference of 1 wavelength, okay, so that is our path difference. And we have a singular wavelength path difference, okay, so that is equal to 1 lambda. And therefore, as our path difference is a whole number, they arrive in phase and therefore constructively interfere, okay? We all know that. Sweet. If we take this distance right here, which we said was L, because that's this, right? Okay. And we also take this distance right here. Okay, let's call that X. Okay, and X is the distance between n is equal to 1 and n is equal to 0. Okay? And so therefore, we can see that we make sort of a triangle, right angle triangle, like so. And we said that this angle right here is theta. Well, this angle also is theta. Okay? And the reason why these angles are the same is due to what's called a small angle approximation. So we can write that down. Small angle approx. Now, what is a small angle approximation? Small angle approximation basically says that for really, really small angles, we can say that sine theta is equal to tan theta. Now, you can also do this on your calculator. Let's say we have an angle of 0.5 degrees, and we put that into sine. Sine 0.5, we get 8.7265 times 10 to the negative 3, okay? That's not the full value, that's just to 5 decimal places. But let's do tan 0.5, okay? So tan 0.5 degrees is equal to 8.72687 times 10 to the negative 3. Now you can see that these values are very, very similar. And so therefore we can approximate that sine theta is equal to tan theta. Now, in this case, tan theta is equal to x over L, right? Because, again, tan is opposite over adjacent, okay? And we've already discussed how our path difference is equal to d sine theta. And so, therefore, combining them, we can substitute tan theta, which is x over L, for sine theta, and we get our path difference is equal to d x over L, okay? Now, remembering that d is our slit separation, right? So that's that value right there. And obviously, I discussed x is this value and our L is this value, okay? And also, we've said previously that our path difference to find a maxima is equal to n lambda, and so therefore our n lambda is equal to dx over L. And so therefore, we have a relationship between our path difference and our x value. Let's say we have another maxima way up here. Okay, so that's our n is equal to 2. We are going to have light rays that converge like so, like this, okay? And let's say we have, again, another perpendicular line. And so this time, our path difference is 2 wavelengths, okay? So therefore, our path difference has increased from 1 to 2. And as our slit separation, our d has remained the same because the slits hasn't moved. And our L value hasn't changed because that's just the distance between the slits to the wall. Therefore, the only thing that must change is our x value, and as you can see, our x value has indeed changed. It has increased. Okay? So that is how we can approximate our light rays to be parallel, and that's because of the scale that we're working with, like I said previously, and so therefore we can make our small angle approximation and say that sine theta is equal to tan theta. Okay? So now, if we look at this double slit that I showed in the previous video, you can see that when we compare it to our diagram, it's not as clean cut as it might seem, alright? We can see here that even though we theoretically have a dark spot there, we can see there's a lot of light bleed, okay? Like the light is bleeding out, even up top, right? It's not a clean cut dark spot, okay? And so realistically, it's not that this whole thing is dark. We really only have a dark spot for like a fraction, and in between we have like intermediate interference or intermediate destructive interference where it's not quite interfered fully, but it's not as bright as our maxima, okay? And this is where we come along with the idea of a diffraction grating, all right? A diffraction grating. And so what a diffraction grating essentially is just a piece of glass with many, 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 many slits. All right, it's like laser precision. All right, so laser precision slits cuts into glass piece. And with our diffraction grating, our equation of n lambda is equal to d sine theta also holds up, okay? And so for this diffraction grating, the slits are much closer together. And when I mean much, like these are very, very close slits, okay? So our d value is dramatically smaller, okay? And also the pattern is much clearer, okay? I'll go into what that means later. And also the pattern is much more spread out, okay? Now, the pattern being much more spread out makes sense. If we have a smaller d value, a much, much smaller d value, that means our sine value must be larger, and so therefore the angle between each maxima must be greater. However, the pattern being much more clearer, what does that mean? All right, we can see that in this diffraction grating, rather than having that light bleed, the sources are much further apart, like I said, but also the sources, you can see that they're much, much more well-defined. It's almost a perfect circle. If we look at some other examples, we can see this example right here. Now, this is a multi-dimensional diffraction grating. You don't have to worry about that for NCEA. We'll just be doing one-dimensional, right? So it would just be this. So just imagine that these top ones and these bottom ones don't exist, and just focus on this middle one. You can see how the light is much, much more defined and less light bleed, right? This light bleed is mainly due to how bright that central maxima is, which I'll go into later as to why the central maxima is brighter, all right? But you can see even with these outer ones, they're just much, much more defined and much more spread out. So now also for diffraction gratings, we're not usually given a d value. What we're usually given is an n value, and that n value means lines per millimeter. And for example, that might be, let's say 600 lines per millimeter. Okay, so then how do we get our d value? Well, we know that our d value is measured in meters, right? Because it's the slit separation, so it's a distance value. However, lines per millimeter, that means that the unit for this is lines per millimeter, okay? And so in order to get our d value, we can simply just take the inverse of this. And so obviously this is also measured in millimeters, but our d value is measured in meters, so we need to make that conversion by doing times 10 to the 3. And therefore we get 1.67 times 10 to the negative 6 meters, and that is our d value. And so from this, we can say that in order to convert from our lines per millimeter to our d value, we can say that d is equal to 1 over n, okay? And like I said previously, our d value is much, much, much smaller than if we were to have a d value for the double slit, right? Times 10 to the negative 6, that is absolutely tiny. All right, so why is the central maxima the brightest? You saw in those pictures that the central maxima was the brightest by far, and everything else was slightly more dim, okay? Well, if we imagine we go all the way back up here, our central maxima is our n is equal to 0 antinodal line. When we have two sources, all that just means is that the two sources exactly align and have a path difference of 0. Now, for the diffraction grating, we have thousands of sources, all right? So even though we only have one light ray, we can think of each slit producing a source. We can see that in our double slit experiment, we only have one light ray, okay? One laser, that's a laser, just ignore. We only have one laser producing one light ray. However, the two slits produce what looks to be like two sources, okay? So we have thousands of sources, and all those sources meet at the n is equal to 0 antinodal line. So if we have thousands of sources and every source constructively interferes at that n is equal to 0 antinodal line, therefore that is going to be the brightest, right? However, on the edges, so we have our brightest middle, on the edges, we can see that although we still have maxima, they were much, much more dim. So this central maxima, all light, combines. However, for these other maxima, right, we can imagine there's going to be more than one maxima right here, okay? For diffraction grating, a lot of the light is going to be destructively interfering, right? Because there is a lot more sources, there is a lot more destructive interference happening, because it's more likely for a wave to be out of phase than it is for it to be perfectly in phase, okay? So because there is a lot of destructive interference, a lot of the light gets cancelled out, and we only get some of the light coming into this maxima, okay? And so it's not the full intensity. And this effect is greater the further you get out, okay? And so that is why we get our central maxima to be the brightest, and the ones around it are slightly less bright, but still pretty bright. And then by the time we get to the outer ones, they are pretty dim, but still, you can still see a maxima, okay? Now, a common exam question you might get is that, it's pretty common, it's pretty much in every exam. What happens when we put white light through a diffraction grating, okay? Now, if we put white light through a diffraction grating, like I said, the central maxima is the combination of all light, and so that central maxima, okay, this central maxima is going to be white, okay? However, the maxima on the sides is going to be different, okay? So these are regions of maxima, okay? If we have a diffraction grating here, and then we have a source of white light coming in. As we know, white light consists of all frequencies of light, so that is from violet to red. Okay, and as we know, violet has the highest frequency and therefore its wavelength is the shortest, and red light has the lowest frequency and therefore its wavelength is the greatest. And because n lambda is equal to d sine theta, because violet has a smaller wavelength, it's going to diffract, that diffraction angle is going to be smaller, okay? So violet is going to diffract less, okay? If we have our central line right here, this angle is going to be smaller, and so that's going to be violet. And so we can call this theta v, for theta for violet. However, red is going to diffract the most. And so this angle right here, we can call theta r, is going to be the greatest, because red has the greatest wavelength, and therefore its theta value is going to be the largest. Okay? And so this is going to be red. Now, everything in the middle, from yellow to green to whatever, is going to be somewhere in between, okay? But for your examination, you only need to really worry about red and violet. You can just basically say that violet diffracts the least, red diffracts the most, and then everything in between follows the same pattern, okay? And so each maxima is a spectrum of light. So this is our n is equal to 1, and this is obviously n is equal to 0. And so our n is equal to 2 will obviously have the same thing, where we have violet on this side and red, and then everything else in between. Okay, and so as you can see here, this is what I mean. We have our violet, you can't really see the violet, it's more like blue over here, but we have our central white, okay, and then we have our violet / blue, and it goes all the way to red, okay? And over here, you can see multiple maxima. So again, this is our n is equal to 0, n is equal to 1, n is equal to 2, and then you can kind of see an n is equal to 3 there or maybe that's just a glare on my computer, but whatever. Okay? Alright, and that will be it for interference.